Welcome to this Eriksholm update. Have you ever considered how hearing aids in the future are going to address the number one complaint of hearing aid users out there in the world, namely tackling speech and noise and communication challenges in difficult listening situations? Imagine a future where your hearing aids are able to adapt themselves to you and your needs. I want to introduce now Peter Asbjørn Leer Bysted, a scientist working at Eriksholm and looking at specifically this problem. So welcome, Peter. Please tell us about how you're looking at trying to make hearing aids more effective in a more diverse number of situations and places.
So let's talk about how they currently work. So how we currently deal with this problem of denoising is that we train, for example, a neural network, and we train it in a lot of different scenarios. Once this is trained, this is deployed in a hearing aid and then shipped to the end users. So when it's trained on all these scenarios, it learns to be equally good at everything at once, but maybe that's not what we want. Maybe we want systems, hearing aid systems, that are good at this particular situation you're in right now. So how do we approach this problem, going from a static model to kind of an adaptive model? Well, we could be inspired by how the brain actually processes speech. When we listen to speech, we adapt continuously. Consider, for example, if you go to a lecture and you hear someone with an odd accent. Maybe you don't understand what they're saying. Maybe they confuse beer with peer. So slightly using context, you start to slowly adapt. And after a few minutes, you will actually notice that maybe you don't pay any notice to their accent anymore. So you slowly adapt. So what we have going on there is in fact that we have a general model of speech in our brain, but it adapts slowly.
So a little bit like my poor pronunciation of your name.
Exactly,
Okay.
exactly. Yeah. So to do that, you need two things. You need a system that is able to learn from the environment, and then a system that is able to adapt. So those are the two things we're trying to do.
Okay. So then please tell us how you see hearing aids helping us in other ways then.
Well, the particular way I would go about looking at this is that, let's say that most of the time, hearing aid users encounter the same scenario. So they talk to their partners, they talk to their colleagues, they talk to their caregivers or something else. These are voices that recur again and again. So maybe we should exploit that and get hearing aids that are good at actually enhancing the speakers we meet again and then again and again. So you will end up with not a generic static device, but a device that does my partner's speech enhancement. And
I guess that's, maybe not a simpler problem, but a more contained problem because there's a more limited number of people you interact with as opposed to all the noises and sounds that are out there in the world that you might want to suppress.
Yeah, maybe it is, but maybe noises are also similar and voices can in fact be very, very different, both in terms of accents, but in the rhythm and even what words they say, their lexical content, so to say. So it's very rich speech. But even if you look at yourself, me and James, we have different heads, we have different bodies, and that also shapes how sounds are received at the microphones. So in fact, we also would like to adapt that so it could sound more natural and help you with localization. So there's a lot of ways to approach this subject.
So then what are then, from your perspective, the sort of practical challenges that you're facing in your project?
Well, number one, there are three, but let's start with the first one. It's the technical challenge. You have two systems. You have a learning system, a system that tries to extract the context of what is going on. And then you have the adaptive system. So the adaptive system needs to be efficient, but it also has to be not wrong. Because this is, secondly, it's a medical device.
Exactly.
So we cannot do whatever we want, and we should not make it worse for the user. And we also want to stay within the bounds of what is prescribed by the audiologist. And last but not least, there's also the end user, the hearing aid users' concerns of their privacy and that they can trust what is going on. So we also want to have algorithms that actually work on the device, perhaps while you're sleeping, while it's charging, and so on and so on. But ideally, it shouldn't leave the ecosystem that you have
for sure.
and get sent to some server in somewhere you don't know, and with recordings of your partners. That is not going to fly.
That's a no-go.
That's a no-go. We want it to stay within the bounds of your own.
So keep trust by maintaining privacy by
Exactly.
design.
Yeah.
So, well, thank you very much, Peter. That was very interesting and very, very inspiring.
Thank you for having me.
Imagine your hearing aid is able to seamlessly adapt to your intentions. In other words, it can intuitively do what you want without you having to give an active input to the device. I want to introduce now Niels Overby, a scientist working at Eriksholm who's trying to look at exactly this problem and approaching it by using external microphones and how they can interact with your hearing device. Niels, welcome. Can you please tell us a little bit about the very, very practical problem that you're actually trying to solve with your project?
Yes, absolutely. So the overall problem is the cocktail party problem. Now imagine you are at a busy restaurant and there are multiple ongoing conversations.
Mm-hmm.
There might be background music, some noises, maybe the acoustics aren't that great either. And you are trying to have a conversation with a very specific person,
Yep.
or maybe a group of people.
Yep.
Now for a normal hearing person, this would not be that difficult. They can manage these situations. They've been in thousands of before, and it's somewhat easy. Maybe it's some bit challenging, but it's possible.
Yeah.
So for a person with hearing impairment, this can be an incredibly difficult situation.
Mm-hmm.
The voice that they're attempting to attend is blending in with all the background noises, thus making it very difficult, and they might have to ask their conversation partner to repeat themselves, asking what again and again, and it's a very frustrating situation.
Mm-hmm.
Even if they're wearing hearing aids, sometimes they cannot still focus on the person.
Still a number one complaint. So.
It really is, yeah. So this environment can be extremely frustrating to a person with hearing impairment,
Mm-hmm.
since the voice that they're attempting to attend just kind of blends in with all the background noises, thus making it incredibly difficult. They might have to ask, what did you say, again and again, and it becomes so frustrating up until the point where they might decide that they don't want to participate in these kinds of events anymore.
Yep.
They might want to prefer to stay back and kind of isolate themselves. So if we can tackle this problem, we could hugely improve their quality of life.
Yeah. So in essence, you're trying to solve this classic challenge
Mm-hmm.
of the cocktail party problem that many, many hearing scientists and many audiologists are deeply aware of.
Yeah.
And your technical approach is to say, well, let's try and take some external microphones, couple that with a hearing aid, and then press a magic button, train a network, and suddenly you've got a solution? Or what is it? What is the research thorny challenges that you face?
Absolutely. So the cocktail party problem has a lot of different solutions, and we have gone in many directions to try and solve this.
Mm-hmm.
My approach is to include an external device.
Yeah.
We'll have an external microphone
Yeah.
device system with multiple microphones, and we can put it on the table.
Mm-hmm.
With the multiple microphones, we can point different directions. We could add improved processing power, thus being able to use artificial intelligence to further advance the system. Here we would like to do a series of tasks, really.
Mm-hmm.
We would like to be able to separate the candidate speakers within this acoustic scenario.
Mm-hmm.
From that, we would like to combine it with the actions of the hearing aid user,
Mm-hmm.
such that we can determine who among the candidate signals are relevant to the hearing aid user.
Yeah. So basically, you've got a system that can separate the different sounds that are in that scene, and then by using some kind of gesture or some motion in the user,
Yes.
then you can use that as a channel selection. That's the intention.
Exactly.
Yeah.
So somehow manage to make the signals from the users, it can be any really movements or whether they're looking or any other kind of things that makes it comparable to the signals from the external microphone.
Mm-hmm.
That way we can select what might be the most relevant
Yeah.
to the hearing aid user.
Yeah.
Now when we have figured out what signal is relevant, we have to take into account that it's recorded over here, but what they hear is up in their ears.
Yeah.
So we need to be able to send the signal from the external microphone into the ears in a way that does not seem intrusive,
Yeah.
such that it is as natural as possible.
So it doesn't feel like your head is in the middle of the table, basically.
Exactly.
Yeah. Okay.
So to kind of summarize, we have this three major task in my project really,
Yeah.
which is to separate the different sources, being able to select who are you attending,
Yeah.
and then present it the most natural way as possible. And if we can succeed that, I believe we can drastically improve the quality of life for these hearing impaired listeners who would always stay at home, but now they can participate in these social gatherings.
Fantastic. I wish you the best of luck with it. Super interesting project.
Yeah, thank you.
imagine your hearing aid had a little version of yourself or a little model of you sitting inside it that was able to continuously make judgment calls on the microscopic speech intelligibility, in other words, word for word or even phoneme for phoneme, or speech quality assessment, or even how fatiguing or how effortful sound is in a given moment. Now imagine that hearing aid was also, while it's making those judgments, is able to continuously update all of its internal settings to sort of optimize the sound processing for you. Panos Apostolidis is working at Eriksholm as one of our scientists, and he's looking at exactly this problem. Welcome, Panos. Please tell us a little bit about your project.
Yes, of course. The conceptual idea of my project is continuously asking the hearing aid user what is the right sound right now.
Yeah.
And then, based on their answer, on their output, we can adjust or adapt the processing of our hearing aid in order to provide the best possible sound under diverse acoustic or noise scenes.
Yeah.
Of course, as you can imagine, something like this is not realizable in a real life because, of course, we cannot bother the hearing aid user
People
at
get
all
pretty
times.
frustrated if
Exactly.
you continuously ask them that.
So what was our idea? Our idea was to replace the user with a mathematical or a computational model of them that represents aspects of human perception, like speech intelligibility, sound quality, or even listening effort, as you mentioned. The benefit that we can get from this is that we can ask this model multiple times in a second, and then based on its output, we can then adjust our processing, and we can even adjust thousands or millions of parameters at this time.
So Panos, how is this then different from how hearing aids process sound today?
There are actually two directions that differentiate our approach from existing hearing aids. First, the structure or the configuration of hearing aids so far is found in an offline optimization process. So through controlled environments or through tests in the lab. Then we deploy this processing algorithm to the hearing aid, and we expect it to perform similarly out in the wild, out in the real world, as to the tests that we performed in the lab.
So it's completely frozen and then it's deployed.
Without doing any further validations, pretty much. Our approach or our idea is to introduce a mechanism that allows the hearing aid to listen to its output, evaluate it, and then adapt its processing in order to perform even better.
Yeah, for you as an individual.
Exactly.
Yeah.
And as a second point, what I wanted to add is that most hearing aids actually try to optimize for criteria that have to do with pure audibility.
Yeah.
And even though we want, of course, the sound to be audible, it's not enough in many cases, as a user might be able to hear the sound but then not actually understand the content of speech. So what we aim to do is to optimize directly for some aspects that are directly related to human understanding or human perception, like speech intelligibility.
Interesting. So then what are the sort of the key challenges then that you're facing with this project?
Well, first, there is the challenge of building such models of human perception. It's not an easy task. People have researched it for years, and we know that it's not perfect because they cannot capture every aspect of human perception. But let's say that we can manage to do that, or we can even use some already established models of human perception. Then there is the challenge of bridging the gap between human understanding and machine understanding, because maybe we are able to optimize for these models so we can score very high in regards to them, but then when we bring this sound and we have it evaluated by a hearing aid user, they're not happy at all, because it might not sound realistic, it might sound synthetic or fake. So there's pretty much a series.
So there's quite some challenges to get through, but again, super exciting direction, and I wish you all the best of luck with that as well.
Thank you.
Bringing deep neural networks into modern hearing aids has led to some significant improvements in signal-to-noise ratios. However, pretty much all the devices on the market today make use of what we call a post filter. In other words, they just take a single microphone or audio input and then they denoise those. And prior to that, they would have some kind of spatial filtering where you would have multi-microphone input. So Robert Rehr is a scientist working at Eriksholm, and he's looking at this problem of using multiple microphones as inputs to deep neural networks for essentially denoising. In other words, what he's actually doing is he's trying to combine this spatial filtering or beamforming and the post filter into one processing block. So welcome, Robert. Can you please then explain how multi-microphone speech enhancement is done, and particularly using AI, and how that's different from the traditional approaches that we're using today?
Yeah, maybe let's start with the traditional approaches. And yeah, these algorithms that we have been using for many, many years, they are actually in some way a bit special because they can be split into two parts.
Yep.
So we have one part, which is, we call this, we could maybe say this is like a filtering in room, in space, basically.
Mm-hmm.
And what this part does, like the first part, it basically allows me to pick up view. Like I can look into a certain direction and the signal will pass through without modification. And at the same time, like from all other directions, like the sound will be removed as much. And this part basically merges like the multi-microphone signal into a single microphone.
Yeah.
And then we have like something that we call the post filter, where we have like basically a filter that every time tries to filter out the main noise components.
Yeah.
But this distinction, or this split into these two parts, might vanish actually in the future with a machine learning-based algorithm, because like a very simple way is actually to provide like a neural network, like all the microphone signals, and ask to provide the target signal, which could be your speech, for example, and basically you just remain with like one black box which does all the processing at once.
Yeah. So then, what are the advantages then of taking this kind of AI-based approach as opposed to doing these classical methods?
And again, I would like to start with the classical approaches, and they are basically based on very simplifying assumptions. For example, we try to model noise with a Gaussian distribution.
Yeah.
And while like these simplified models, I mean, based on that, we can do some mathematical evaluation, and they led to like, algorithms that basically could do the job. They could remove the noise, but still, like these algorithms, because this is a really simple assumptions that we have here, might gloss over actually the reality, like all the details that we actually have in sound, and that might be important to our hearing aid users. And this is where the machine learning part comes into play, because neural networks, when you provide them all the examples like of the sound out there in the world, they can basically extract all the nuances and details that we cannot capture like with our simplified model, and can therefore obtain like a much higher performance that we also can see in our experiments.
So then how do you see the future of hearing aid development when you consider these sorts of changes in hearing aid processing?
It's always, of course, hard to foresee the future, but I think like one trend that appears to be realistic is that we will start to replace like more and more of these classical algorithms that we have on the hearing aid with machine learning driven algorithms. And the simple reason is just like that we think that we can gain more performance out of that.
That's just because they can really get at the actual statistics of the situation in a better way than making assumptions.
Probably, this is what we believe that can be done. And this comes with still with certain challenges, and like one of them is that we don't have like a real model for the hearing loss or for hearing impaired people. So we don't actually exactly know what sound they actually need. And coupled to that is also like the what is actually the intention of the user. So what does the user or the hearing aid user want to listen to? And this is like also like a problem that we still need to cover. And maybe one of the most important things is like if we like cover everything up like with these black boxes, like with these neural models, that we still have to ensure that this is like can be understood by the hearing care professionals and also the users themselves what the device is actually doing.
Yeah. Fantastic. Very, very interesting, Robert, and thank you very much for sharing with us your insight.
You're welcome.
Thank you very much for watching this Eriksholm update. For me, it's incredibly inspiring to work with so many fantastic scientists and work on so many interesting topics here in Eriksholm. And I hope at least you took some of that away with you today. And see you next time.